A hotel that's always full, yet somehow never out of rooms. A cat that's both dead and alive. A time traveler who erases their own past. These aren't riddles, they're paradoxes, the ultimate glitches in logic that make reality stop making sense. Get ready to step into the space where reason collapses, truth twists, and the universe starts arguing with itself. This is Every Paradox Explained. Paradox 1. The Liar Paradox. Imagine someone says, "This sentence is false." Now think about it. If the sentence is true, then what it says must be accurate, which means it's false. But if it's false, then it's actually telling the truth, which makes it true. There's no stable answer. It flips forever between true and false, breaking the basic rule that every statement must be one or the other. Here's another version. Take a card. On the front, it says, "The sentence on the other side of this card is true." Flip it over, and it says, "The sentence on the other side of this card is false." No matter which side you start with, you end up in an endless loop. What the liar paradox teaches us is that self-reference, when something talks about itself, can crash logical systems. It's led philosophers to build hierarchies of truth and new types of logic that can handle these traps. Paradox 2. The Barber Paradox. In a town, there's a rule. The barber shaves all and only those who do not shave themselves. So here's the question. Does the barber shave himself? If he does shave himself, then according to the rule, he's someone who shaves himself, so he shouldn't be shaved by the barber. But he is the barber. Contradiction. If he doesn't shave himself, then he's someone who doesn't shave himself, so according to the rule, the barber should shave him. But he is the barber. Another contradiction. This paradox, developed by philosopher Bertrand Russell, exposes a flaw in how we define sets. It showed that some definitions, like the set of all sets that don't contain themselves, are inherently contradictory. Modern set theory was built specifically to avoid this trap. Paradox 3. Ship of Theseus. Imagine you have a ship. Over the years, you replace every single plank, every nail, every sail. Eventually, not a single original part remains. Is it still the same ship? Most people say yes, it's the same ship because it's had continuous existence and function. But here's the twist. What if you took all the old planks you removed and rebuilt them into another ship? Now you have two ships. Which one is the original? One has continuity of existence, the other has all the original parts. This paradox forces us to question whether identity is about material, history, function, or something else. It's not just philosophical. It applies to everything from personal identity to digital copies of consciousness. Paradox 4. Sorites Paradox. The heap. The Sorites Paradox is about vagueness. Start with a heap of sand, let's say 10,000 grains. Now remove one grain. Is it still a heap? Of course. Remove another. Still a heap. Keep going. At what exact point does it stop being a heap? If you say removing one grain never stops it from being a heap, then you'd have to say that even one grain is a heap. But that's absurd. If you draw a line, say at 1,000 grains, that feels totally arbitrary. Why not 999? Why not 1001?
Paradox 5. Zeno's Paradox. Achilles and the Tortoise.
Achilles, a fast runner, races a tortoise. Being a good sport, he gives the tortoise a head start. The race begins. Achilles runs to where the tortoise was, but by the time he gets there, the tortoise has moved a little bit forward. So Achilles runs to that new spot, but again, the tortoise has moved a bit more. This repeats infinitely. Every time Achilles reaches where the tortoise was, the tortoise is somewhere new. So it seems like Achilles can never actually pass the tortoise. Of course, in reality, Achilles does pass the tortoise. So what's going on? The resolution comes from calculus and the concept of convergent series. The distances Achilles covers, half the gap, then half of that, then half again, add up to a finite total. Infinite steps can happen in finite time when each step gets smaller fast enough. Paradox 6. Zeno's Dichotomy Paradox. Here's another one from Zeno, closely related. To walk from point A to point B, you first have to get halfway there. But before you can get halfway, you have to get a quarter of the way. And before that, an eighth. And so on, infinitely. Since there are infinitely many steps, it seems like you can never even start moving. Again, the answer is that infinite subdivisions of space don't prevent motion. They just show that space and time are continuous and divisible. The sum of infinitely many shrinking distances can still be finite. Paradox 7, Zeno's Arrow Paradox. Imagine an arrow in flight. At any single instant, in time, the arrow occupies a specific position in space. It's not moving to where it is, and it's not moving to where it isn't. It's just there, stationary at that instant. But if the arrow is stationary at every instant, and time is made up of instants, how does the arrow ever move? The resolution is that motion isn't a property of a single instant, it's a property of intervals. Velocity is the rate of change of position over time, and you need at least 2 moments to define it. Paradox 8, Hilbert's Hotel. Let's jump into infinity with one of the most mind-bending paradoxes. Imagine a hotel with infinitely many rooms, numbered 1, 2, 3, and so on, forever. Every single room is occupied. The hotel is completely full. Now a new guest arrives. Is there room? You'd think no, but actually yes. The manager simply asks every guest to move from their current room to the next room number. The guest in room 1 moves to room 2, the guest in room 2 moves to room 3, and so on. Now room 1 is empty, and the new guest checks in. Even weirder, an infinite bus full of infinitely many new guests shows up. Can they all fit? Yes. Move every current guest from room N to room 2N. Now all the odd-numbered rooms are empty, and you have infinitely vacancies. This paradox shows that infinity doesn't behave like large finite numbers. A set can be the same size as a proper subset of itself. Paradox 9, Thompson's lamp. Here's a paradox about completing infinitely many tasks, called a supertask. You have a lamp with a switch. At the start of a minute, you turn it on. After 30 seconds, you turn it off. After another 15 seconds, you turn it on again. Then off after 7.5 seconds. And so on, flipping faster and faster. You perform infinitely many flips within 1 minute. Question, when the minute is over, is the lamp on or off? There's no answer. The sequence of states, on, off, doesn't converge to a final state. The lamp's state at exactly 1 minute is simply undefined by the setup. This shows that some infinite processes don't have determinate endpoints, even when they finish in finite time.
Paradox 10, the Ross-Littlewood Paradox. You have an urn. At 1 minute to midnight, you add balls numbered 1 through 10 and remove ball 1. At 30 seconds to midnight, you add balls 11 through 20 and remove ball 2. At 15 seconds to midnight, you add 10 more and remove ball 3. You repeat infinitely. At midnight, how many balls are in the urn? Surprisingly, 0. Every ball you ever added has a specific number, and you eventually removed it. But wait, at each step, you added 10 and removed 1, so the count kept growing. How can it end at 0? Because with infinity, the order and the limit process matter. The number of balls approaches infinity, but the set of balls remaining at the limit is empty. Paradox 11, Monty Hall Problem. You're on the Dame show. There are 3 doors. Behind one is a car. Behind the other 2 are goats. You pick door 1. The host, who knows what's behind each door, opens door 3 to reveal a goat. Now the host offers you a choice. Stick with door 1 or switch to door 2. Should you switch? Most people think it doesn't matter. 50-50 chance either way. But that's wrong. You should switch. Switching wins 2/3 of the time. Here's why. When you first picked, you had a 1 in 3 chance of being right. That means there's a 2 in 3 chance the car is behind one of the other 2 doors. The host's reveal doesn't change your original pick's odds. It's still 1/3. But now all that 2/3 probability is concentrated on the remaining door, so switching doubles your chances. Paradox 12. Birthday Paradox. How many people do you need in a room for there to be a better than even chance that 2 share a birthday? Most people guess something like 180. The real answer? Just 23 people. With 23 people, there's about a 50% chance of a match. With 70 people, it's over 99%. Why? Because we're not asking if someone matches your birthday. We're asking if any 2 people match. With 23 people, there are 253 possible pairs. Each pair has a small chance of matching, but there are so many pairs that the cumulative probability shoots up fast. Paradox 13. Simpson's Paradox. Imagine a hospital tests a new treatment. When you look at men, the treatment helps. When you look at women, the treatment helps. But when you combine the data, the treatment looks worse than doing nothing. How is that possible? It's about hidden variables and group sizes. Maybe sicker patients were more likely to get the treatment, and more of those patients were in one gender group. When you pool everyone together, those differences in severity skew the result. Paradox 14. Berkson's Paradox. Selection effects. Suppose you notice that among hospitalized patients, smokers seem to have better outcomes than non-smokers for a certain disease. Does that mean smoking helps? No. The problem is you're only looking at people who made it to the hospital. Smoking might make you less likely to survive long enough to get there in the first place. Paradox 15. Newcomb Problem. There are 2 boxes in front of you. Box A is transparent and contains $1,000. Box B is opaque. A superintelligent predictor has already predicted your choice. If the predictor thought you'd take just box B, it put $1 million in there. If it thought you'd take both boxes, it left box B empty. The predictor has been right 99.9% of the time in the past. Do you take just box B or both boxes? Causal decision theory says take both. What's in the boxes is already determined, so you might as well grab the extra $1,000. Evidential decision theory says take only box B. Your choice is evidence of what the predictor foresaw. So one boxing signals you're the type who gets the million. There's no consensus. It's a paradox because both arguments feel compelling. Paradox 16. Grandfather Paradox. You build a time machine, go back and stop your grandparents from ever meeting. That means your parents are never born, which means you're never born. But if you were never born, who went back in time to stop your grandparents? This is the classic grandfather paradox. Paradox 17. Bootstrap Paradox, also called the ontological paradox. A time traveler goes back and gives Shakespeare a copy of his complete works before Shakespeare wrote them. Shakespeare publishes them as his own. Later, those works are put in a book which the time traveler eventually takes back. Where did the information originate? Paradox 18. Predestination Paradox. You learn about a disaster and go back in time to prevent it, but your actions in the past are precisely what caused the disaster. For example, you warn someone to avoid a certain road, so they take a different route, and that's where the accident happens. This paradox suggests that in a single, self-consistent timeline, the future can cause the past, and all your attempts to change history just fulfill it. Paradox 19. Polchinski Paradox. A billiard ball rolls into a wormhole and emerges in the past on a trajectory that knocks its younger self off course, preventing it from entering the wormhole in the first place. Contradiction, right? Not necessarily. Physicists have shown that there are self-consistent solutions. The angles adjust slightly so that the ball's past and future selves interact in a way that still allows the loop. The paradox teaches that if time travel is possible, the laws of physics might enforce consistency rather than allow contradictions.
Paradox 20. Schrödinger's cat.
one of the most famous paradoxes in physics. A cat is in a sealed box with a device. If a quantum particle decays, poison is released. If it doesn't decay, the cat lives. Quantum mechanics says that until you observe the particle, it's in a superposition, both decayed and not decayed at the same time. So before you open the box, is the cat alive or dead?
Paradox 21. EPR Paradox in Bell's theorem. Einstein, Podolsky, and Rosen proposed a thought experiment to show quantum mechanics might be incomplete. Two particles become entangled. You separate them by a huge distance and measure one. Instantly, the measurement outcome on the first particle seems to determine the outcome on the second faster than light could travel between them. Einstein called it spooky action at a distance and thought it meant there must be hidden variables we don't know about. But decades later, physicist John Bell proved that no local hidden variable theory can reproduce the predictions of quantum mechanics. Experiments confirmed it. Nature really is non-local in this sense. Entangled particles are correlated in ways that defy our classical intuitions about separateness and causality. Paradox 22. Gibbs Paradox. If you have two containers of the same gas at the same temperature and pressure, separated by a partition, removing the partition shouldn't change the total entropy. But naively calculating it in classical stat mech suggests the entropy increases, the mixing entropy. The resolution, particles are indistinguishable. Once you account for quantum indistinguishability properly, the extra entropy vanishes. Paradox 23. Olbers Paradox. Why is the night sky dark? If the universe is infinite, static, and uniformly filled with stars, every line of sight should eventually hit a star. The whole sky should be as bright as the surface of the sun. But it's not. It's dark. The resolution, the universe is not static and infinite. It has a finite age. It's expanding, and light from distant stars is redshifted. Stars also have finite lifetimes. All these factors mean distant starlight is dimmed or hasn't reached us yet. Paradox 24. Paradox of choice. You'd think more options make people happier, but studies show that too many choices can lead to paralysis, regret, and lower satisfaction.
Paradox 25. Jevons Paradox. When cars become more fuel efficient, you'd think we'd use less fuel, but the opposite happens. Cheaper driving means people drive more, and total fuel use can actually increase. This is Jevons Paradox. Efficiency can backfire by boosting demand. Paradox 26. Friendship Paradox. Your friends have more friends than you do. It's mathematically true. Why? Popular people appear in more friend groups, so they're overrepresented in everyone's network. Paradox 27. Paradox of tolerance. A tolerant society values freedom, but what if some people want to destroy tolerance itself? If you tolerate the intolerant, they can dismantle your society from within. So to preserve tolerance, you may need to be intolerant of intolerance. Paradox 28. Moore's Paradox. It can rain while you don't believe it's raining. But you can't say, it's raining, but I don't believe it's raining. Why does this sound absurd? Because saying something implies you believe it. It's a contradiction in communication, not logic. Paradox 29. Raven Paradox. Testing all ravens are black seems simple. Find black ravens. But logically, this equals all non-black things are non-ravens. So a green apple should confirm it too. That feels wrong. The paradox shows logical equivalence doesn't always match evidential relevance. Paradox 30. Unexpected Hanging Paradox. A prisoner is told he'll be hanged on a surprise weekday. He reasons it can't be Friday, he'd know by Thursday, so not Friday. Same logic rules out Thursday, then Wednesday, and every day. Then the executioner arrives Wednesday, and he's completely surprised.
Paradox 31. Crocodile Paradox. A crocodile steals a child and says, "I'll return your child if you predict what I'll do." The parent says, "You won't return my child." If the crocodile returns the child, the prediction was wrong. If it doesn't, the prediction was right, so it should return the child. It's a logical trap.
Paradox 32. Lottery Paradox. A lottery has 1 million tickets. One will win. It's rational to believe ticket 1 will lose, and ticket 2, and ticket 3. So you rationally believe every ticket will lose, even though one must win. Probability clashes with consistent beliefs. Paradox 33. Diamond-Water Paradox. Water is essential. Diamonds aren't. Yet diamonds cost more. Why? Price reflects scarcity, not importance. Water is abundant, so each glass has low value.
Diamonds are rare, so each one is valuable. Paradox 34, paradox of thrift. Saving money is smart for you, but if everyone saves more, spending drops. Businesses cut jobs, incomes fall, and total savings decrease. Individual wisdom becomes collective harm.
Paradox 35, Service Recovery Paradox. When a company messes up but fixes it brilliantly, customers can be more satisfied than if nothing went wrong. Exceptional recovery exceeds expectations and builds trust.
Paradox 36, Stability-Instability Paradox. Nuclear weapons prevent major wars through deterrence, but this stability makes smaller conflicts more likely because both sides know escalation is unthinkable. Peace at one level, war at another. Paradox 37, Opposite Day Paradox. If someone says it's opposite day, does that mean it's not opposite day? The statement flips itself infinitely. It's the liar paradox in playful form. Paradox 38, Preparedness Paradox. Prepare extensively for a disaster, and when it's not so bad, people say you overreacted, but it wasn't bad because you prepared. Success makes the threat look smaller in hindsight. Paradox 39, Interesting Number Paradox. The smallest uninteresting number would be interesting for being the smallest, so it becomes interesting. Same for the next one. By this logic, every number is interesting. Paradox 40, Pinocchio Paradox. Pinocchio says, "My nose will grow now." If true, it shouldn't grow, but then he lied, so it should. If false, it should grow, but then he told the truth, so it shouldn't. No stable answer exists. Paradox 41, Braess Paradox. Adding a road to ease traffic can actually make traffic worse. Drivers choose routes that help them individually, creating a worse overall pattern. More capacity doesn't always mean better flow. Paradox 42, Parrondo's Paradox. Two losing games can combine to make you win. Game A loses, Game B loses, but alternating between them produces wins. Losing strategies can interact to create winning outcomes. So, there you have it. Every major paradox explained. From self-referential loops that break logic, to infinite hotels that never fill up, from quantum cats that are alive and dead, to time travelers who erase their own existence, from statistical traps that fool professionals to economic puzzles where good intentions backfire. Paradoxes aren't glitches in reality. They're stress tests, ways of finding the edges of our concepts, our language, our logic, and our intuitions. They show us where our models break down and where new thinking is needed. Some paradoxes have been resolved, others are still debated, and a few may never have a single right answer. They might just reveal that the world is stranger and richer than any one framework can capture. Which paradox messed with your brain the most? Drop it in the comments. And if you want to deep dive on any of these, whether it's infinity, time travel, quantum mechanics, or decision theory, let me know. Thanks for watching. And remember, the edge of logic is where the most interesting ideas live.